Hi, gang. It's Dr. Barone. I'm here to finish up the final part of the CNS. We've got some important things left to do. We still have to do the dementing diseases and we have to do the tumors. Important stuff that will be on your USMLE coming up. So let's make sure we do it and do it well. Now let's start with the dementing diseases. Dementia. The most common cause, 60% of all cases, are Alzheimer's. So we finished Alzheimer's in the last tape. That was a very important one. Now we're going to do some weird ones like Pick's disease. That's always an interesting disease. It's the most common form of frontal temporal lobular degeneration. For short purposes, some people call it frontal temporal dementia. But I love it when the name tells me the answer. Frontal temporal lobular degeneration. I wonder what's going to degenerate. Maybe the frontal lobe, which is important for personality. Maybe the temporal lobe, which has my memory, my hippocampus. So I kind of like this. So frontal temporal dementias are going to have frontal problems with executive thoughts. So things like inappropriate behavior. In fact, some people say Pick's disease, they act like jerks. They act like a prick. Yeah, so Pick's acts like a prick. Now, again, they're not bad people. This is the problem when your brain degenerates. You may do things that you would normally never, ever do. So it's kind of a silly way to remember it, but Pick's can act like a prick because they could do things that are very appropriate. They could be jerks. They also get very disinhibited. So they'll get naked. They'll get very promiscuous. They'll lose judgment. They don't think about the consequence of their actions. Yeah, they can't foresee the consequences of things they're doing. So again, that's why they say Pick's can act like a prick. Now, in addition, they're going to get dementia. So the temporal lobe is where your hippocampus is. So you're going to wind up with dementia and basically inappropriate behaviors. Now, the changes in personality and behavior usually precede the dementia. So that's an important clue because that can help you distinguish Pick's disease, which is kind of rare, versus Alzheimer's, which is an incredibly common cause of dementia. It's common. So look for those personality and behavioral changes. And often you have to talk to the family. The family will tell you, I don't know what's wrong with Uncle Joe, but he's been acting like a real beep. Now let's go to the pathology. What do you expect to see when you look at the frontal and temporal gyri? Well, they're going to really degenerate. They're going to be really, really thin. So we'll see cortical atrophy in the frontal and temporal regions. In fact, it gets so thin, the gyri, they're like thin like the edge of a knife. So they call them knife edge or knife like blade thick gyri. So they're really, really thin, like the thickness of a knife. Now that's because of extensive loss of neurons and intense gliosis. Lots of astrocytes start proliferating. Again, gliosis is a very important clue to tell you, hey, there's something wrong in that area of the brain. Now, the remaining neurons will often have Pick bodies. And every time there's a body in the brain, they're going to ask you, what's it made of? What's that Pick body made of? Well, these are round cytoplasmic inclusions containing tau filaments. So you'll see tau accumulation. Sometimes you'll even see tau tangles, but usually they become round and we call them Pick bodies. Now, you'll also see cytoplasmic accumulations of ubiquitinated TAR DNA binding protein 43, TAR, T-A-R, TAR DNA binding protein 43. Now again, DNA binding proteins, they should usually be in the nucleus, right? Now they're accumulating in the cytoplasm, which is kind of abnormal. Now this is a very important clue, but it's not causing it because this is seen not just in Pick's disease, it's also seen in Lou Gehrig's disease, amyotrophic lateral sclerosis. So important to test. TAR DNA binding protein 43 accumulation. Think of Pick's disease, frontal temporal dementia, and think of Lou Gehrig's disease, amyotrophic lateral sclerosis. Two diseases where it's accumulating. So again, is it causing it? No. Whatever's causing the disease is leading to the accumulation of this TAR DNA binding protein. So it's an important finding, but it's not actually causing the disease. It's like a consequence. So let me show you some pictures. Here's a nice stain for tau. Notice you're seeing accumulation of tau in the cytoplasm. So this one's kind of forming more of a tangle, but usually they form round spherical Pick bodies. So if we notice inside this nucleus, you see a pretty round, dark thing. That's a Pick body. This round thing, Pick body, Pick body. So again, it's basically tau, but it's round, spherical. So they call it a pick body. And again, we see tau best on silver staining. It lights up really good. Now we can also do immunostaining to look for accumulations of TAR DNA binding protein 43. And notice here's the nucleus. In this case, it's accumulating in the cytoplasm. See that? Accumulation of TAR DNA. That's abnormal. Now you're supposed to see it in the nucleus, but they're also seeing inclusions there too. So notice they have accumulations of it. It's all piled up here. And again, that's abnormal. So cytoplasmic accumulations are very abnormal. And then you see nuclear, well, that's what it should be, but it's also accumulating there too. So whatever is causing this disease is leading to accumulation of this protein. And it's not unique. Lou Gehrig's will have it too. But if I see it on the exam, I've got a 50-50 chance of getting it right now. TAR DNA binding protein accumulation, Lou Gehrig's, which is amyotrophic lateral sclerosis, versus Pick's disease. All right, now back to something that's high yield. Alzheimer's is high yield and Parkinson's disease is high yield. This is common. About 2% of the population has it. So this is an important thing to know. Now, we're going to start with a concept. The term is Parkinsonism. That's not the disease. That is the clinical syndrome where you get tremor, like a resting tremor, like pill rolling. I often call it the money sign. Moolah, show me the money. So you get these pill rolling, resting tremor. You get rigidity, like a cogwheel. It goes cogwheel rigidity. You get slowing of movements. We call that bradykinesia. And they get instability of their gait. So they shuffle. They get this fenestrating or shuffling gait because it's hard for them to start their motion, stop their motion. They get very unstable. So Parkinsonism is a clinical syndrome with these findings. It's usually due to Parkinson's disease, which is destruction of the neurons. But you can also see Parkinsonism if basically you have any problem with dopamine. So for instance, what if you take a drug like a dopamine antagonist? Well, you knock out dopamine, you're going to get the same Parkinsonism clinical findings. Okay, so these are just the term for clinical findings. All right, now Parkinson's disease is when you actually damage the nigrostriatal dopaminergic system. So you're going to lose the pigmented dopaminergic neurons of the substantia nigra. So what color does the substantia nigra turn? Well, it's supposed to be black because of the pigmented neurons, but it's going to lose it. It's going to become pale. So you're going to see pallor of the substantia nigra. That's a very important clue on the exam. It turns very pale because you've lost these pigmented neurons. And this is going to lead to the motor syndrome, Parkinsonism. Now, this can also be induced, as I mentioned, by drugs. So dopamine antagonists will do it. And some toxins, like pesticides. All our wonderful food now is genetically modified. Yes, they modify the crops to put in the genes for pesticides. So that way, when the bugs come to eat the corn, well, they eat the corn, they get sick, and they die. So they'll stop eating the corn. But guess what? In the corn are pesticides, which are you're going to eat too. But you're not a bug. You'll be fine. Well, guess what? If you're putting a lot of pesticides in our foods, eventually that's going to hurt our brain. So that's not good. So high pesticide exposure has been associated. And this is an interesting one. MPTP. It's a really long chemical name. But this occurs when you break bad. You break bad. You go into your basement laboratory, just like Walter White, and you try to synthesize illegal drugs. Yeah, but not meth this time. Meperidine. This is Demerol. It's an opiate. Demerol. So if you go in your basement lab and you try to make it illegally, well, unless you're Walter White, who gets 99% purity, you're going to get some of this contaminant. So when I take this drug, I'm going to get high, but then I'm going to damage my substantia nigra and wind up with Parkinson's. So there's been a handful of cases where this has occurred, but it's been on the USMLE. So remember, young people using drugs, they made it themselves, then they get Parkinson's. Remember, MPTP. And by the way, since we know about this, now we can use this drug to make experimental models. So we can give it to animals, destroy their substantia nigra, and the animal will get Parkinson. And then we can do experiments and test and learn. So this is a pretty important chemical, MPTP. All right, now how common is this? It's about 2% of the population will eventually develop Parkinson's. Wow, 2%. Okay, not us. We're perfect. but another 100 people, 2 of them are going to get it. Wow. And it usually occurs between the 6th and 8th decades of life. So 50s, 60s, 70s, that's usually where you see it. Unless, of course, your name is Michael J. Fox. Michael J. Fox got it young. He was filming the movie Doc Hollywood, and on the set, he started getting early symptoms of Parkinson's. Yeah, what's interesting though is on the same set, 2 other people, young people, got early onset Parkinson's. Hmm. Hmm. I don't want to hear Barone said Michael J. Fox used illegal drug. No, Barone said, hmm, hmm. When you see a cluster of young people getting early onset Parkinson's in a Hollywood movie set, it's possible. Maybe somebody got some drugs, right? They made it themselves or they got it on the cheap. And they said, come on, try this. It's really good. They came in, maybe shared it, and a couple of people may have gotten it. Again, I don't know. I don't know. But when you see young people cluster cases, you got to think about maybe possibility of illegal drugs. Now, we all know Muhammad Ali, right? Muhammad Ali also got it too. Remember when he was older, he stayed against the rope and he'd do the rope-a-dope. When that guy got tired, the dope got tired, I beat him, the rope-a-dope. So this is a Parkinson's support group. Now, if you remember the Pope, John Paul II, John Paul II had it. He'd shuffle up to you with his cog rigidity, his resting tremor, saying, I bless you, my son. The cogwheel, cog rigidity. Yeah, classic findings. And of course, what killed him? Well, do you remember the old man's friend? No matter what puts you in the bed, whatever makes you bedridden, you're going to aspirate and bronchopneumonia. That's a pretty common cause of death for most of these neurodegenerative diseases because they're all going to wind up bedridden and then they die of pneumonia. All right, and of course, former Attorney General Janet Reno, the Attorney General for this dude. Be careful, Janet. Ooh, Bill. Watch where his hands are. Slick Willie. Oh, man, we almost had him in the White House again. How cool would that have been? He would have been in the White House with nothing to do. Oh, boy. They'll say, Hillary, we need a lot of interns. No way. That would have been so cool. All right, now, Parkinson's disease. What do we need to know? Well, clinical features we should know is you're trapped. You can't move. You're trapped. The only movement you get is the resting tremor. Otherwise, you're stuck. You can't move very well. So you get diminished facial expressions. So they often say it looks like you're expressionless, like you're wearing a mask. Expressionless, mask-like face. Very common. Now, they also get slowing of the voluntary movement. They get the fenestrating, shuffling gait, where they get the short, accelerated steps. They get the stoop posture, bent over. They frequently fall because of instability. Cogwheel rigidity is a very classic finding. And they get the resting tremor, often manifesting as a resting, pill rolling like tremor. I call it the money tremor. Moolah, show me the money. Now, can Parkinson's patients get dementia? Absolutely. It's one of the dementing diseases. But the dementia is usually seen years after. So 8, 9, 10 years after diagnosis, that's when they get dementia. They get it late. Now, I'm bringing this up for a reason. Parkinson's, 10 to 15% are going to get dementia, but they get it late. What if I said it looked like Parkinson's and they got dementia basically at diagnosis? So Parkinson's and dementia at diagnosis, then you want to think about a disease called Lewy body dementia. Lewy body dementia, because this is going to look very similar. It looks like Parkinson's disease. It looks like Alzheimer's disease. So you got the movement of Parkinson's, you got the dementia of Alzheimer's. So it looks very similar, but they get the dementia early, usually at diagnosis. They're also going to have visual hallucinations. And that's one of the hallmarks. They're going to see things that don't exist. They're not there, but they see people and animals and they think they're real. So that's very characteristic as well. And they also tend to get orthostatic hypotension. So when they stand up, their blood pressure drops and they fall because of orthostatic hypotension. So here's the problem. Parkinson's can fall. They can have falls because of instability, not because of blood pressure, because of instability. Parkinson's can also get dementia like Alzheimer's, but they get it later. They get it later. This has it at the same time. They don't have visual hallucinations. So really, those are the two key things to telling it apart. Look for the early onset of dementia and the fact that they're seeing things. Because falls and Parkinsonism, that's in common for both. So in the past, Lewy body dementia was underrecognized. We used to diagnose it and think it was Parkinson's. So most cases, we called it Parkinson's, but it was really Lewy body dementia. So this is one of those diseases that's increasing just because we're recognizing it. In the past, we thought it was Parkinson's or Alzheimer's. It got misdiagnosed. So we'll talk more about that next. That'll be coming up next. Now, to treat Parkinson's, what we're going to try to do is improve your movement. So to do that, we're going to try to increase dopamine. So we can do that by putting in electrodes and do deep brain stimulation to stimulate the neurons. Or we can give you L-DOPA, so forms of dopamine. Now the problem is, these are going to improve movement, but they're not going to stop the neurons from dying. So this is going to stop working. So by stimulating the neurons and they all die, well, deep brain stimulation is eventually going to fail. And if neurons keep dying, I'm going to have to give you more DOPA, more DOPA. The DOPA level that I give you is not going to be enough. I'm going to have to keep increasing it until finally I can't give you enough. So that's bad. So really, these treatments are for symptoms. They really don't change the disease. So you want to make $1 million? I want to be a billionaire, so beeping bad. Well, you can make millions putting out a sex tape, but you're not really going to make the world much better. Well, maybe you will, depending on the quality of your tape, I guess. But you can definitely make the world better if you can figure out a way to stop these neurons from dying. Just stop them from dying. If you can make them grow back, that would be even better. But just stop it from progressing and you will make millions of dollars and you'll help so many people. Because remember, who is affected by these dementing diseases? Not just the patient, but the whole family. The family watches their loved ones suffer and they can't do anything. They also have to take off work. They got to call in sick. They got to pay a lot of money for the health care and all these people to watch them. It is a devastating disease for the entire family. So if you can figure out what to do with these diseases, you'll make a lot of money. And the brain is the great unknown. It's the great unknown. And why not you? Why can't you make a great discovery? You're young. You're fresh. You haven't been beaten down by medicine. Yeah, you'll see on the wards, it's like, do it my way. Do it my way. Why? Because I said so. Do it my way. Do it my way. You're still thinking. So great discoveries are often made by medical students when they're starting their career because they ask why still. And they may see something, oh, you do that over there? Why don't you do that in this scenario? They see things and they apply it to scenarios we didn't think of. So why not you? And then I can say, I knew you when. I knew you when you were still a medical student and not a Oscar-winning, Grammy-winning, Nobel Prize-winning doctor. I know you can do great things, and you will. You will. All right, now let's talk about some of the genetic causes, because most cases are sporadic. We don't know why the pigmented dopaminergic neurons die. It's probably oxidant damage. It's probably free radicals, but we don't know. But there are recessive and dominant hereditary forms. So that's important. If it's running in the family, we should certainly know about that. Now, those are probably going to be more early onset and more severe. Now, there's 5 genes that we've found have been associated with Parkinson's disease. 5 genes. The first one is probably the most important for testing, and that's the alpha-synuclein gene. And that makes sense because alpha-synuclein is going to accumulate in Parkinson's and create what's called Lewy bodies. So it would make sense if you mutate the gene, its protein's going to accumulate much quicker and you can get these Lewy bodies. So that makes sense. And this is a lipid-binding protein that normally associates in the synapses, and it's going to accumulate and become a major component of the Lewy body. So how do I remember alpha-synuclein and Lewy body? Well, I've got kind of a naughty way. Do you remember the VMAs? Do you remember the twerking incident where Miley Cyrus was twerking a teddy bear with her pill rolling movement? Her butt was wiggling back and forth. The twerking, that's a pill rolling movement. Pill rolling, that's a resting tremor of her butt against the teddy bear during the Blurred Line songs. Now, my buddy loves it when she gets naked, but most people would say it's a sin. It's a sin to show your lewd body like that. It's a sin to show your lewd body like that. So alpha-synuclein is the major component of Lewy bodies. It's a sin to show your lewd body. I know. My friend loves it when she gets naked. Every time she gets naked, goes on net wrecking balls, he's very happy. So there's kind of like blurred lines between what's a sin and what's not a sin. Blurred lines. I'm on a roll today. All right, now another gene is the LRRK gene, leucine-rich repeat kinase 2. This is seen in dominant sporadic cases, and there's genes that are important for the mitochondria. So if they dysfunction, well, neurons can't make a lot of ATP. Maybe that's the reason they're dying in these genetic forms. Now, one of the genes you should know is the Parkin gene. If I missed that, I should be spanked, right? The Parkin gene. Well, this gets loss of function, and this usually occurs in the very young forms, the juvenile recessive forms, when they get it really early. And this one kind of makes sense because the Parkin gene is an E3 ubiquitin ligase. So if I mutate this, you're not going to ubiquitinize and break down proteins. So if I don't get rid of misfolded proteins, they're going to accumulate in my brain and clog up my brain. All this protein, like the alpha-synuclein, when it's misfolded, it'll accumulate and get Lewy bodies and damage the brain. So it makes sense the Parkin gene, loss of ubiquitin ligase, would play a role here. Okay, so these are the two I would want you to know. Okay, but again, most cases are not genetic. Most cases, we don't know why the neurons get damaged, probably free radicals. All right, now here is the classic pathology. This will be tested like crazy. So first thing they could do is show you a gross picture of the substantia nigra, and it's supposed to be black. Well, it's now going to be pale. And not just the substantia nigra, the locus coeruleus will also be pale too. It's supposed to be pigmented, but you're going to lose these pigmented dopaminergic neurons. Now, if we look at a normal midbrain, this is the substantia nigra right here. It's a band-shaped group of neurons right here. They're nice and pigmented, aren't they? Well, guess what happens in Parkinson's? You start losing that pigment. And I'm pretty sure you can see there ain't much pigment left anymore. That's because the dopaminergic neurons are gone. They're pigmented, and you've been now lost. And they'll get replaced by gliosis. Now, if we look with the microscope, under the microscope, we'll see there are some cells remaining, and inside their cell body, we see these round pink inclusions. Pink is protein, right? So these are Lewy bodies made of alpha-synuclein. There are also some neurofilaments, and ubiquitin is in there as well, but it's mostly made of alpha-synuclein. So Lewy bodies, it's a sin to show your Lewy body. And they're in the cytoplasm, they're pink, they're round to elongated inclusions. So pigmented neurons lost and Lewy body accumulation. These are the two hallmark features. Loss of neurons, any neurons that are left have Lewy bodies. Now, can I see the substantia nigra very well? Can I see it losing pigment on an MRI or CT? Well, I can see the midbrain, but I can't see the color of it. So radiology, imaging is not very useful for Parkinson's. It'll be useful for Alzheimer's. You'll see generalized atrophy, especially in the temporal lobes. It'll be important for PICs. The frontal and temporal lobes will atrophy. But in Parkinson's, imaging is not really that helpful. And we're not going to really see all that much because you're losing pigment, hard to see that. All right, so it's basically a clinical diagnosis, and clinical diagnosis plus response to the DOPA agents. Now, fun ways to remember these two classic findings. Muhammad Ali. Muhammad Ali was born in 1942 in Louisville, Kentucky. What kind of bodies? Lewy bodies. Makes sense. Louisville, Lewy bodies. And when he got older, he'd stay against the ropes and let them get tired. He called it the rope-a-dope. I'll stay against the rope, let the dope get tired, and I'll beat them. What it didn't know is what dope was being lost with each blow. He had dopaminergic neuron, rope-a-dopaminergic neuron. So Lewy bodies and loss of dopaminergic neurons, this is your classic features. All right, now let's do a disease that is often misdiagnosed as Parkinson's. It's called Lewy body dementia. So, you think you're going to see Lewy bodies here? Yep. You think you're going to get dementia? So to me, it looks like Parkinson's disease movement problems plus Alzheimer's dementia. But then I got to add more to it because Parkinson's can get Alzheimer's. They can get the dementia type features, not like Alzheimer's. So I want to know if it's like Parkinson's plus Alzheimer's, and it's going to be early onset. But they're also going to get the visual hallucinations plus hypotension. So they get a lot of falls. So you want me to pick this one? Tell me it looks like Parkinson's movement. Tell me it looks like the dementia of Alzheimer's. And then tell me they see stuff like people and animals that aren't there and they're falling. That's what I'm going to pick. So let's go to the clinical right here. This is a progressive degenerating dementia of the elderly. So it looks like a lot like Alzheimer's. You're going to get deficits in attention and executive function. You're going to get fluctuation from day to day. So some days are better than other days. But you're also going to see the motor features of Parkinson's. So the same shuffling gait, the same cognitive rigidity, the same resting tremors. So that's why it can get diagnosed in the past as Alzheimer's or Parkinson's. That's how it used to get diagnosed. Now it's like if you looked at it, it seems like an epidemic. No, it was occurring before, we just didn't notice it. Now we're actually diagnosing it properly. Now, again, the key for the diagnosis is that when they present, not only do they have the motor, but they have the dementia as well. Parkinson's gets the dementia later. In addition, look for the orthostatic hypotension, which means they repeatedly fall and have syncope. They faint when they stand up. Just blood pressure drops. And then finally, look for those visual hallucinations. Now, I made it red because if you want me to pick this on an exam, it's usually what you're going to have to give me. So visual hallucination of people and animals, and they are well formed. They are vivid. They are detailed. They really can't tell it from reality. I had a patient with this once, and I said, what happened? Well, I'm doing something, and then I look over, and there's my friend. Now, before I talk to her, I stick my cane. And if they go, ow, I'm like, ooh, sorry. I just want to make sure you're there before I talk to you. If the cane goes through it, then I don't talk because I know it's not there. But it's so real, I can't tell it from reality. I got to put my cane in. Another patient I was seeing their animals. They were seeing their dogs in the room. Now, they can't hear them, but they see them in the room. And it's so vivid, they think they're there. They think they're there. So that's really a key feature to look for. Now, for histology, we're going to see the same Lewy bodies. So Lewy bodies, I always think Parkinson's first. But if it's not Parkinson's, it could be Lewy body dementia too. Again, it's made of alpha-synuclein. Now, the symptoms overlap with Alzheimer's and Parkinson's, so that's why misdiagnosis is so darn common. Now, who had it? Well, Lewy body dementia was in Casey Kasem. It's American Top 40 Countdown. We're going to count down the land's greatest hits. Do you remember Casey Kasem? Yeah, well, he had this. They thought it was Parkinson's. No, he actually had this Lewy body dementia. And if you remember, not only did he do the American Top 40, but he also was the voice of Shaggy. Do you remember Scooby-Doo? He was the voice of Shaggy. Zoinks! Let's go get a Scooby snack, right? Shaggy, he was the voice. Now, do you remember? Shaggy and Scooby were always the one who saw the ghost. And everybody's like, what? I didn't see it. So they saw stuff that nobody else saw. Oh. And then they get scared, like, zoinks! And they fall. And then they get up and they'd run. They'd fall when they see it. They're like, they fall down, then they run. So classic. They saw stuff that's not there, and then they fall. Classic. And unfortunately, he passed away. Very sad. Casey Kasem, voice of Shaggy. Now, another one is Mrs. Doubtfire. Jumanji, Good Will Hunting. Yeah, Robin Williams, the great Robin Williams. No, John, he had Parkinson's. No, he had Lewy body dementia. They misdiagnosed it as Parkinson's. Now, think about this. If you can't move properly, you're kind of trapped in your body, that's depressing. A lot of people get depressed with this. If you have Alzheimer's dementia and you can't remember, that's depressing too. So you can't move, you can't remember. And then you see stuff that you realize isn't there. You see people and they're not. He must have thought he was going insane. And he wasn't going to tell anybody. He didn't tell anybody. He was seeing things and he didn't tell anybody. He didn't tell his wife because he thought he was going nuts. And falling down, he was falling down too. His wife said he was all bruised. And she asked him, what happened? He said, it was dark. I bumped into the wall. No, he was getting up and falling down. He was having orthostatic hypotension. So in retrospect, it's clear he had Lewy body dementia. And that's the reason. I mean, it makes sense. I mean, Parkinson's bad enough. Then you add some dementia to it. You add things, you're seeing stuff that ain't there. You're falling down. Your body's betraying you. No wonder he took his life. It makes sense now. It makes a lot of sense. It's very sad. That's Lewy body dementia. Again, it's increasing because we're recognizing it. All right, now here's an example of a disease that's incredibly rare, but the board likes to test it. Incredibly rare. Huntington's is not a common disease at all, but it makes great TV. It's great for ethics discussions, and it's great for USMLE questions. So sometimes they do that. They ask things that are incredibly rare, and they ask it a lot. It's weird. So Huntington's disease, I think we talked about this already with the triplet repeats, but we'll remind you of what's important. Now, it's autosomal dominant, so you can give this to half your kids, and you don't want to give this to your kids. It's bad. They're going to get progressive movement. Remember those choreiform dance-like movements, and they're also going to get dementia. Usually the chorea comes first because the caudate gets damaged first, and then the rest of the neurons, you get dementia. And they also tend to get very violent and very abusive. And we're not sure why, but violent and abusive behaviors are very common. So violent and abusive. Okay, now let's talk about the movement. The motor problems usually come first. You get this jerking, hyperkinetic, sometimes dystonic movements of basically any part of your body. So they describe it as appearing like dance-like. So this hyperkinetic movements. So they describe it as dance-like, but they don't start with the big dances. They start with the small muscles in the face first. So yeah, it looks like tics, but tics are in one spot. This is moving around. So it looks like facial grimacing, facial twitching, and the hands. The hands will start writhing. They may describe it as a bag of worms, or one vignette said it looked like the patient is playing a piano playing movement. So these are the movements that come first. And then later on, they get the bigger vogue. They get the bigger dance-like movements later. Okay, so sometimes it's confusing to students because they expect to see the big movements. No, it's just facial grimacing and twitching and writhing hands initially. Hey, this is purposeless movements. This is dance-like movements of my fingers. Yeah. Now, that usually occurs first, and then later on they tend to get to dementia. Some individuals can also develop some Parkinsonism, some movement problems with bradykinesia sometimes and rigidity too. But most of the time it's chorea. Now let's go to histology. This is degeneration of the striatal neurons of the caudate and the putamen. So if I can only ask you one part that atrophies the most, you say the caudate atrophies the most. Now remember, these neurons are GABAergic. They're inhibitory. So if you lose inhibition of your basal ganglia, you lose inhibition, you're going to move it. That's why they move so much. They lose the GABAergic nerve in the caudate. Now, unfortunately, this disease keeps getting worse with time, so it's relentlessly progressive, and there's nothing we can do right now. Nothing. Now, they get onset usually in the 30s to 50s, but every generation will present earlier and more severely because of the anticipation. So if your grandparents got it in the 50s, then your parents will get it in the 40s, then you'll get it in the 30s, your kids will get it in the 20s, and so forth. It keeps getting younger and younger, and usually it expands when you're passed on by the dad. So when you get it from your dad, it really progresses quickly. Now, the average course is usually 15 years to wind up dead. So you don't last very long. So these patients watch their parents die. They know in them it's going to be more severe and more earlier onset. So don't be surprised when these patients try to commit suicide because they know what's coming. Once they start getting symptoms, they're like, I don't want to suffer. So suicide or suicide pacts. Remember, this is genetic. Your family members could have it, all of them. So you tell your brother and sister, if you get it, I won't let you suffer like mom and dad. I will end your suffering. If I get it, please don't let me suffer. So suicide pacts, very common. And again, for USMLE purposes, if they ask you, can you help me commit suicide? Can you just, or don't kill me, just leave a syringe with a lot of morphine? No, that's physician-assisted suicide. We can only do it if the vignette specifically says you're in a state that allows physician-assisted suicide. Make sense? So again, the rule for the USMLE is you don't help anybody assist in suicide unless it specifically says you can. Yeah, first do no harm. First do no harm. Now, the death usually comes when they become bedridden and they get pneumonia. They aspirate. Again, that's a common cause of neurodegenerative people ending. It's the old man's friend. Now, if we remember Huntington, well, in an H is a 4. So Huntington's disease gene is on chromosome 4, and the Huntington's gene is called HTT. That's a good name for the gene, right? HTT, Huntington. Love it. So the HD gene, which is the HTT gene, that's what they call it. HTT gene is on chromosome 4, and it codes a protein called Huntington protein. Makes sense. Now, what happens to it? A repeat. You're going to get CAG, CAG, CAG repeating hundreds of times in the first exon. That's where it's going to accumulate. Remember, exons are expressed. So that's not the stuff that's junk that gets thrown out. That's part of the gene. So this is going to make a protein that gets really, really long. Really long. Now, normally the Huntington's disease gene has 6 to 35 copies of this CAG repeat. When it expands beyond 35 copies, now you'll start to get disease symptoms. And the more copies, the longer it is, the worse it is. So the longer the number of repeats, the worse it's going to be. And again, when it's passed on from the dad, it usually expands very rapidly and you get anticipation. Now, I know they're going to ask this. What does the CAG repeat do inside the Huntington protein? Well, it makes it really long and gives it a toxic gain of function. So that's cool. It doesn't knock it out. Most of the triplet repeats not get knocked out. This is a gain of function. So it becomes really long and becomes toxic. So this poor mutated protein basically gets ubiquinated, it starts accumulating, and it starts damaging the brain. You start losing neurons. So that's the problem. You start losing neurons, especially in the caudate, but throughout the body. All right, so remember, caudate atrophy gene. Caudate atrophy gene. The atrophy will be in the caudate nucleus and putamen the most. But the rest of the brain will atrophy too. Now, if you remember, the caudate is right next to the ventricle. So when the caudate atrophies, the ventricles become huge. So the lateral and third ventricles become very large, but not because of any pressure. It's because of less brain. So the term for that is hydrocephalus ex vacuole. And they really seem to like to ask this. They usually ask it with Alzheimer's, but anytime the brain atrophies significantly, you can see hydrocephalus ex vacuole, which has normal pressure. There's no problems with it's communicating, no problems. It's just more fluid because less brain. Again, it also happen in Pick's disease too. Pick's frontal temporal dementia, where everything atrophies like knife blades. You can see this too. So not specific, but remember this term when the brain atrophies. Now, since we're losing the striatal neurons in the caudate, these neurons are GABAergic. GABAergic. They're inhibitory. So when we lose them, we're going to lose the inhibition of the basal ganglia. And that's why you're going to move, because you're not inhibiting the motor output. So you're going to move and move and move when you don't want to move. Now, fun way to remember this. Newsflash. There are 4 turkey hunters. They're trapped in their own cage. Don't hunters use cage? CAG expansion? And they're eagerly anticipating release. So that's everything you need to know. So here's the 4 turkey hunters, Dick Cheney, Dick Cheney, Dick Cheney, and Dick Cheney. They're trapped in a cage, and they're trying to get out, but they can't. Now, why 4? Well, chromosome 4. Why hunters? Because Huntington's. Why cage? Because hunters use cages, right? That's what's repeating. And of course, anticipating release. Every generation is more early and more severe. Now, why turkey hunters? Because what did turkey say? Gabba, 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 GABAergic, gabba, gabba, GABAergic. All right, now here's a great way to test it. Here's half of a normal brain. Here's half of your patient's brain. What's wrong with your patient? Well, clearly the whole thing is atrophied. Compared to this brain is really small. That's why they get dementia. But what's atrophied the most? The caudate. So let's do normal anatomy first. Normal neuroanatomy. Notice this white area here. This is called the internal capsule, right? The fibers come through here and then they radiate. They radiate to the gray matter. Very good. So that's the internal capsule. Now, what is this nucleus that almost looks like a lens? Doesn't it look like a lens? Yeah, that's called the lenticular nucleus. That's the lens of your brain. This is the putamen and globus pallidus. Now, do you remember what disease? What disease will the putamen and globus pallidus atrophy the most? Do you remember what disease? I'll give you a hint. You might want to use D-penicillamine, a copper chelator. Good. Copper overload, Wilson's disease, hepatolenticular degeneration, hepatolenticular Wilson's. That's what's going to atrophy. So you better know your neuroanatomy. I'm warning you now. You got to go back to what Mike told you. All those the different parts of the brain, you better be able to find them in imaging. Because if I give you a patient with Wilson's disease, I'll show a CT or MRI and ask you A, B, C, D, E, which part of the brain is going to atrophy. So you need to know what's going to atrophy. Now, do you remember if you have carbon monoxide poisoning? If you have carbon monoxide poisoning, you don't get enough oxygen to your brain, you get necrosis. Which part? Globus pallidus. Globus pallidus. So this is very important for carbon monoxide poisoning. You can wind up with globus pallidus necrosis. So that's important. Necrosis of globus pallidus, carbon monoxide poisoning. All right, but we need to get to the caudate. This thing over here, this big old thing, this is your caudate nucleus. Notice the caudate is right next to the lateral ventricle. So when this caudate atrophies like it did here, notice the hydrocephalus. Hydrocephalus ex vacuole. Now, did the putamen and globus pallidus atrophy? Yeah, they atrophy too. But the caudate, I barely see it. The caudate's like really the atrophy the most. But putamen does atrophy, globus pallidus atrophy a little bit too. And then the rest of the brain atrophies as well. That's why they get dementia. Okay, so classic picture. Now, another way I could test it is this. If I really want to see if you know this, here's what I could do. I could say, here's a normal brain, and say injury to this area occurs in a disease located on which of the following chromosomes? So atrophy and damage to this area occurs in a genetic disease that involves which of the following chromosomes? So number one, I have to know this is caudate. I have to remember what's a genetic disease with caudate. Oh, that's Huntington's. Huntington's. Then I have to remember what's the gene. It's HTT, and it's on chromosome 4. Chromosome 4. So that's a nice way to test it. Now, you just did it now, so it should be pretty easy for you. But in a few months, when you take the exam, you got to remember these associations. This is a genetic disease. Their brothers and sisters may have it too. Autosomal dominant. Check the brothers and sisters. Now, let's take a look at this picture. There's an intranuclear inclusion here. Do you see it? Here's the nucleus. Inside the nucleus, this inclusion is lighting up right there. Yeah, this is staining with ubiquitin. Ubiquitin. See that? Aggregates of ubiquitin is accumulating there because this abnormal protein is toxic. It's accumulating in the neuronal cell and it's damaging the cell. It's getting ubiquinized. It's getting damaged. It's damaging the cell. That's the ubiquinized Huntington protein that's accumulated. All right, now, do you remember USMLE question? What house character tested herself for Huntington's? Well, 13. 13. Her brother had it, and her brother was suffering. So she actually went and she assisted suicide. She actually killed her brother because her brother was suffering. He asked her to, and so she said, I'm a doctor. Okay, I will help you. And she helped him die. And then House is like, well, maybe you got it too. It's autosomal dominant, 50% chance. Don't you want to know? Don't you want to get tested? Here, let me see your cup. I want to get some DNA. He tried to like secretly test her, and he badgered her so much. She said, you know what? Maybe I do want to know. She got tested, and sure enough, she had it. She had it too. Yeah. So then she said, forget this. I'm going to enjoy my life. See, would you want to know if you had a disease that has no treatment? Well, screening is controversial because we only screen if we can do something. If we can't do anything, so screening is an individual decision. You go to the family members and you say, hey, listen, if you have this disease, we can't do anything. Do you want to know or not? So you have to do informed consent and then see if they want to get tested. So it's an individual test. If we had a treatment, screening would be standard, right? We'd always screen family members. But since we can't do anything, it's kind of controversial whether you screen or not. So the answer is an individual decision. Would you want to know? Oh, hell yeah, you would want to know. Would you continue to study for the USMLE? Hell no, you take out a second medical student loan and you go to Ibiza, baby. If only a few years to go, boom, I'm going to go party. I'm going to enjoy the rest of it, right? Right? I know. Now, if you worked at 7-Eleven, like most of the world, do you know most of the world, when they're done with work, they don't have to do anything. No studying at night. They just go out and enjoy themselves. Weekends, they're all theirs. I know, you don't even know what a weekend is. Weekend, no, that's free work day. It's like I don't have to go to lecture. I got all day to study. I know, it's so sad. So we would definitely want to know. But the rest of the world, some people wouldn't want to know. It's like, just leave me alone. I'm enjoying my life already. I know. All right, now for fun, what Nintendo character should be tested for Huntington's because he's always moving? He's always for hunting for Princess Peach. Bring, bring, it's me, Mario. Mario. He's always moving. Bring, bring, bring. He can't stop moving. He's got Korea. And he's always hunting for Princess Peach, who repeatedly, every game, repeatedly winds up trapped in a cage. Mario, save me. Again? Every game I have to save you? I think she's really having an affair with Bowser. She just doesn't want to tell Mario. So she's in bed with Bowser, right? And Mario rings the bell. Oh, quick, it's Mario. Put me in the cage. Mario, he caught me again. I don't know how I was here. I don't know. Every time I got to save her. So that's okay. I like playing the game. But he's always hunting for Princess Peach, who repeatedly, CAG repeats. He gets inhibited by that spiny turtle. Look at the spines. Yeah, the spiny neurons of the caudate. Those are the ones that are GABAergic. Those spiny neurons. They call them spiny because they got these spikes on them. So these spiny neurons, really cool. Those are the ones. So the spiny turtle, the spiny neurons, those are the inhibitory ones. And those are the ones that get lost, right? We're always going to beat him. And then what's the music underground? GABAergic, bring, bring, GABAergic, bring, bring, I love it. Isn't there a new Nintendo out? Is there a new Mario game? If there's a new Mario game, I'm going to buy it right away. Now, should we check his brother Luigi? Well, remember, it's autosomal dominant. Here's the problem, though. Who is your confidentiality with? With Mario. Mario's your patient. You can't check the brother. You can tell Mario, this is a genetic disease. Tell your brother to come in. Or give me permission and I'll talk to your family members. But I can't break confidentiality. If Mario says, I don't want anybody to know, you can't tell anybody. You can't do anything. You just have to let them, until they get symptoms and they come to you, you can't do anything. So it's always confidential. The only time you can break confidentiality with the patient is life and limb threatening. If they're going to kill themselves, you can intervene. If they're going to blow up a school, you can intervene. If they're going to do something that will hurt themselves or others, that's the only time you can break confidentiality. Doctor-patient confidentiality is sacred. So remember that for the exam. Should we check the brother? You got to ask Mario first. And then checking the brother will be an individual decision. We'll go to the brother with Mario's permission, and we'll say, we have a disease here. If we test you, we can't do anything. Do you really want to know? It's up to you. You make the decision. We give informed knowledge, and then they make the decision. Isn't this fun? I love this chapter. All right, now, Friedreich's ataxia, another triplet repeat, another one. And of course, this is going to give us ataxia, Friedreich's ataxia. So they call it spinocerebellar degeneration. Think there's problems in my spinal cord? Think there's degeneration of our cerebellum? You bet. That's why they get all this ataxia. They're going to be in a wheelchair by age 5. They can't walk. Now, this is a recessive disorder, and you're going to have low levels of frataxin protein. So notice, this is a repeat that knocks it out. Huntington's, you made too much. It got too long. It gets ubiquitinated, it accumulates, mess up the brain. Here, you're missing. Yeah, this is because of a triplet repeat, and it's GAA. So always remember it as ga, 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 ga. I remember as Lady Gaga. Ga, ga, ga. Doesn't she have that ataxic dancing? She gets on a bells and goes, da, 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 da. She has this ataxic dancing. I shouldn't talk. She's better dancer than me. So anyway, she has ataxic dancing. That's Lady Gaga. Now this is on chromosome 9. And clinically, they're going to get a progression. Their onset is usually in the first decade of life, so very early onset. And they're going to have gait ataxia. They're going to have clumsiness of the hands. They have dysarthria, which is trouble speaking. That makes sense because you need your muscles to speak. So if you're having discoordination with your muscles, you're going to have abnormal or difficulty speaking. And of course, they're going to be wheelchair bound by 5. Okay, so ataxia. Now, cause of death is eventually become bedridden. You're in a wheelchair first, then you're in bed all the time, and you wind up aspirating. Now, you can also die of cardiac disease. So we should mention that too, because that's pretty important. So pneumonias and cardiac disease. Now, Why did they get the gait ataxia, hand clumsiness, and trouble speaking? Well, because look at all the degeneration of the spinal cord and cerebellum, degeneration of this Clark's column. You get degeneration of cranial nerves. You get degeneration of the cerebellum. The Purkinje neurons start dying, and the motor neurons too. So movement, muscular movement, coordination, spinal cord. You're going to get a lot of neurologic problems here. Now, one of the things you want to look for, since this is a nerve problem, is you're going to see depressed or absent deep tendon reflexes. Yeah, and they can often have a Babinski because these are the upper motor neurons that are being damaged. So Babinski very common as well. So nerves, 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 upper motor neurons. All right, now let's talk about the position, the joint and vibratory sense, because you're losing the dorsal columns. You lose the dorsal columns, you're going to lose position and vibratory sense. And they can also lose pain and temperature and sensation and light touch. So some spinal thalamic problems too. So you're damaging spinal cord, lots of different neurons. Now, here's something I would ask. There's a high incidence of cardiac arrhythmias and congestive heart failure. They usually have a large heart, but here is the big association. It's associated with HOCM, hypertrophic obstructive cardiomyopathy, HOCM. Remember, HOCM was usually a dominant genetic disease, right? It was usually mutations in the beta myosin heavy chain gene. Therefore, you get muscle disorientation. They're all disorganized, so they hypertrophy like crazy because they're pulling against one another. That's HOCM. But HOCM can also be due to this recessive disease, Friedreich's ataxia, as well. So I think that's pretty important to remember. HOCM, usually it's genetic, and in this case, it can be due to Friedreich's ataxia. So what triplet nucleotide repeat disorder is associated with HOCM? Friedreich's ataxia. Ga, 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 ga. Triple repeats in the frataxin gene. All right, now this one we've covered already. Ataxia, telangiectasia, but it involves the brain, so it's worth repeating. Ataxia, clearly going to have problems with your cerebellum. And telangiectasia, on your skin, you're going to have lots and lots of dilated, tortuous vessels. Now, this is another recessive disorder, and the mutation is the ATM gene. Makes sense. Ataxia, telangiectasia, now M squared. You're going to get microbial infections because your lymphocytes are going to get damaged, and you're going to get malignancy like leukemia, lymphoma, and also breast cancer because this gene is very important for sensing DNA damage, and it's supposed to turn on BRCA. BRCA. So if you don't turn on BRCA, well, if you're missing BRCA, you get breast cancer, right? Hereditary breast cancer. So without the ATM gene to turn on BRCA, you can't repair strand breaks. So now you're going to have breast cancer risk. Okay, so again, malignancies like leukemia, lymphoma, because the lymphocytes are accumulating junk, and then breast cancer because they can't repair damage. So ATM gene codes for a kinase that's important for orchestrating the repair of DNA strand breaks. So what it does specifically is it tells p53 to stop the cell, gives you G1 checkpoint, G1S checkpoint arrest, and it tells BRCA to fix the strand break. So that's exactly what it does. It's a sensor gene that's going to turn on the genes that stop the cell cycle and repair DNA damage. Now, how do you get strand breaks? Radiation. So these kids should never see X-rays because if they get X-rays, they get sunlight or they get radiation from an atomic bomb or something, X-rays are going to cause chromosomal damage that they can't repair. So these poor cells are going to replicate with damaged DNA because they can't repair it. So they're going to replicate and replicate and replicate. Now, some of them are going to die because when there's a DNA damage, P3 says, sorry, you can't fix it, you got to die. And then some of them are going to replicate with the damage. So that's why you get breast cancer, leukemias, and lymphomas. Okay, so some of the cells will die. Some of them will proliferate with mutations. You get cancer. That's the problem. You got to fix damage to DNA. Now, onset. Recessive diseases usually present relatively early. So it's early in childhood, usually coming with problems with the immune system. So recurrent sinopulmonary infections, that's very, very classic because the immune system has to proliferate all throughout your life. Well, if they get damaged, they have trouble proliferating. You also get unsteadiness in walking because some of the cells in the cerebellum are going to degenerate and die. So ataxia and infections, that's usually what they start with. Then they start getting trouble speaking, so they get ataxia of their speech. They get eye movement problems. And they start developing telangiectasias, usually on the conjunctiva. That's a classic picture for USMLE. They show the conjunctival telangiectasia, and they also get them in the skin too. Now, associations are very high yield. What are they at risk for in the future? They're at risk for developing leukemias, especially T cell leukemias. They're at risk of developing carcinomas, especially breast carcinomas. But do you remember BRCA1 was also for ovarian? It's also ovarian and prostate too. So breast, prostate, ovary, because of BRCA gene not working properly. Okay, but leukemias and breast cancer, those are the two most likely to be asked. Now, unfortunately, this is just going to keep getting worse because the longer you live, the more damage you get and you can't fix it. So this is a relentless progression to death. And again, they usually die of pneumonia, usually in the second decade. Oh God, that's terrible. Teenagers dying. Never like that. No good. All right, now perfect time to take a break. We'll come back on the next tape and we'll